So it's the end of the second day. I think I should summarize what we have done so far. We have formulated in some precise way the two sides of the geometric Lagrange conjecture. And only this afternoon, we have started talking about the idea of factorization. In this talk, I'm actually going to start working towards the proof of the geometric Lagrange conjecture, or at least the idea of the proof. And I will focus on the left-hand side, which is, for me, D modulus on band G. So that's the left-hand side of the Lagrange conjecture. And the fact of life is that this is hard. This is a complicated category. After all, that's the reason why we're here. And so to try to analyze it, I introduced the idea that was already mentioned in Dennis' talk. It's an idea that Dennis and Dim are proposing to prove geometric Lagrange, which is to embed this category, D modulus on band G, into an easier category. And to reach a little bit ahead, this category will be introduced in talk 4.2. And it's the, just say the name, it's the extended Whittaker category. Today, I'm going to do some preliminary work in order to be able to define this in 2 days. And I should say that the one way to see the importance of factorization is that factorization will come in to explain why this guy is easier than the original guy. So this is the main scheme of the next few talks, at least my talks. And let me emphasize why this is hard. Well, this is hard. One way to see why this is hard is because this group G, or general connective reductive group, is complicated as an object, as a combinatorial object. For instance, by contrast, the modulus on band T is actually easy to understand, and we have described actually band T yesterday and today, except that T was just GM. But let me say it again so that I can see also for T. So I can write this upon choosing a point on the curve as this joint union over the co-characters of T of the T Jacobian times BT. And so we know that the modulus on such an object can be described, although we didn't explain the modulus on a product being the tensor product of the categories D modulus. But I think it's in Nick's notes. All right. So we have this comparison, this hard guy due to G being complicated and this easy guy. And luckily, we can bridge the gap, or at least we can try to simplify this guy by using standard subgroups of G that are simpler than G itself, in that they are closer to being abelian. So, for example, we'll use a lot in this lecture the Borel subgroup of G, a Borel, but I choose it, and yeah, the T Jacobian. So, well, if T was GM, that would be the Jacobian, but and so N is the unipotent radical of B. And I regard those groups are being easier than G because B is solvable and N is unipotent. So how am I supposed to use this structure to simplify, or to at least to cook up something simpler than this? Well, I need to connect B bundles or N bundles with G bundles. And that's a general thing. So let me do in this example. First, so if you have the inclusion of B into G, that induces a natural map of stacks from band B to band G. That's a standard map, and it has a name, which is P, and actually mat frac P. So what does this map to S points? So an S point here is a B bundle, and I will cook up a G bundle by extending the structure extending the structure group, namely just to check if we are on the same page. This is explained in the notes, but I can do the associated bundle construction, which is a scheme by definition is the product of those two things mod out by the diagonal action of B. So that's one construction that we use a lot. And note that I didn't use the fact that this was an inclusion, so I can do it also in the most extreme, the opposite case, where I have the canonical projection from B to B mod n, which is the abstract Cartan torus. And in this case, I have also a standard map, which is called Q, from band B to band T, which does the same. And as a shortcut, so it takes a B bundle and, well, let me write down explicitly. And it spits out the associated T bundle. I will focus more on this map rather than this map in this talk. So, where is this? So let me point out, just as an aside, that the reason why, so the fact that this is an inclusion implies that this map is schematic. On the other hand, this map is not at all schematic. Let me write down for an example that shows it's not schematic, because I will need to use it later in other talks. So the most stupid example is I want to take fiber product with respect to point, and that's the trivial T bundle, and that's the stack of n bundles. So a B bundle with trivial whose associated T bundle is trivial is actually an n bundle. That shows that the map wasn't schematic. And so now we are ready to move on to this Gram project, because we have a map from band B to band G, and yeah. So, but before I go on to the main Gram project, let me describe this map a little bit more. Namely, I'm gonna describe. Let me erase this. I'm gonna describe, because since this map is so important, I'm not gonna. I don't care about B bundles on themselves within themselves, but I care about B bundles within the relation, with this kind of relationship to band G, and that's why I will describe them via the Plücker picture. So what's the idea to relate B bundles to G bundle is kind of stupid. I have point mod B, by this I understand the stack, and I can write it as G mod B, and then it's easy to see that I can, so literally it would be this, but it's easy to see that I can change the parentheses, and there I have the flag variety, and then I will use the Plücker embedding of the flag variety. Just to recall, it's so it's this map. It's an embedding in a big product of projective spaces, where V lambda is the irreducible representation of G corresponding to the dominant weight lambda. And this map allows me to do the following construction. I'm left-handed, so I'm going backwards. I'll try not to do that. Oh, I see. So, I mean, let me now describe the condition that cut out, the relations that cut out G mod B inside this product. I'll describe them in the relative setting, namely, I give the following description of S points on band B. Those are triples where you have PG, PT, and kappa, where so PG and PT are respectively a G bundle and a T bundle on the product of the curve with my test scheme, and that's usually denoted by XS to save a little character with. And kappa is actually a family of maps parameterized by dominant weights. And this map goes from, so if I have a T bundle and I have a character of the torus, I can cook up a line bundle. And then I have a G bundle and I have lambda, so I have the representation associated to lambda. And I can cook up a vector bundle that already came up in Lima's talk in some form or another. And I require that this map be an embedding so it's a sub-bundle embedding, by which I mean that the co-kernel, so the quotient by the image, is also a vector bundle. So, i.e., yeah, so I have a T bundle, and I have lambda. Lambda is a character of the torus, so I can use actually this thing. So I use lambda as a map from T to GM, and then I cook up a line bundle. It would be, I mean, if you want, it would be C lambda PT, if I want to have consistent notation. The representation of T, and I twist it by the line bundle, by the T bundle. Okay, so sub-bundle embedding means that the quotient is also locally free. And I'm not done. So you have a, yeah, it's okay. So those maps must satisfy the Plucker conditions. So satisfying the Plucker relations, and then I need to jump here and say what they are. If I do that, I will never correct my order, so I'm going to jump here. So Plucker relations, first of all, I have K naught. That's a map of, if you think about it, of point bundles, OXS into OXS, and I want this to be the identity. And then I can compare various tensor products. So I have lambda of PT tensor mu of PT. That's equivalent to lambda plus mu of PT. And I can go via the tensor product of the map to the Plucker maps from mu lambda to V lambda PG tensor V mu PG. And here I go to V lambda plus mu PG by kappa lambda plus mu. And then, so this is V lambda tensor V mu PG. And I have a natural embedding of V lambda plus mu inside the tensor product of those two representations. And I want this diagram to commute. And this is just, you write down the Plucker pictures, the Plucker embedding of the flag variety into the product of projective spaces, and then plug it in over the curve. And you get these relations. Great. So now let's come back to our favorite map so far. Let's make a crude attempt to describe Bun-G in terms of D modulus on Bun-G in terms of a simpler category. So we know how to pull back stuff on D modules. So let's just do it. So let's first attempt to describe, well, to embed for the embedding. Just do the pullback, Schrick pullback of D modules from D modules on band G into D modules on band B. And the question is, while I do that, is this an embedding? Am I losing information or not? So the question is this fully faithful? By embedding, I mean fully faithful. Give it 10 seconds, and the answer is no. Otherwise, the talk will be finished. And it's far from being fully faithful. Let's see why. So actually, we can see why without knowing anything about G bundles and B bundles. Yeah, there was a digression, actually. Okay, so I'm going to explain why this is not fully faithful, and I'm going to do it without knowing anything. So there is, I don't know many objects here or here, but I know one object, the canonical object, which is the dualizing sheaf, and it gets pulled back to the dualizing sheaf. So I just need to compute, say on band G, between the dualizing sheaf of band G and itself, and compare it to on band B, between the dualizing sheaf of band G at itself, and actually this came up in SAMS thing. This is everything is canonical. I'm not doing anything, so this must be a canonical thing associated to D modules on band G, to band G itself, and that's its cohomology. Fact. Those are facts, and this is likewise the cohomology of band B. And we see that they are different in zero degree, because this is not, so H naught of D modules on band G is just pi 1 of G, and H naught of band B is the lattice of co-characters. Same as it's the same thing as for the torus, which is this. So we have a problem. This map is not fully faithful because this guy is disconnected, and now we want to try to fix this map, to manipulate it in order to make it fully faithful. And to do that, I need to come back to the function theory version of Langlands conjecture. So to correct this, go back to function theory as opposed to geometry. And so going from function theory to geometry is an art, but going back is an algorithm. What's concretely? So if I take a pre-stack, I associate to it a groupoid, which is the groupoid of its k-value points, or maybe the set if I take isomorphism classes. And to D modules on pre-stacks, I associate functions on sets, say C-valued. And if I need to do something more technical, I will have to change also the field from characteristic 0 field to a finite field, but I don't need it now because I'm just doing something not so refined. So let's apply this procedure to those two players and to this map and see what we have. And then let's draw some conclusions. So first of all, question is what are k points of band G? Answer is probably due to veil. Is we can write that as a double quotient, G evaluated on the adeles mod G evaluated on the integral adeles mod G evaluated on the function field of the curve, where So the ideals, recall, is the restricted product of the fraction fields at each close point. So it's restricted with respect to the rings at those points. O is the product of those OX for X close point. So those notations were introduced by Sam. And K is the function field of the curve. And so why do we have this description? We can leave it as an exercise, but the hint is that any G bundle on the curve can be trivialized away from finally many points, and also can be trivialized on the disks corresponding to those points. So in other words, any G bundle on X is glued out of two trivial bundles, one on an open, one on disks, and that's what this double quotient is saying to you. Great. So that's the same applies for BAM B. And now let's try to describe so now we have functions. So functions on a double quotient, I like to consider them as functions on just the quotient on the right that are invariant with respect to G of K. So I'll write it as that. Functions on BAM G of K as functions that are G of K invariant on GA mod G of O. And then same for BAM B. Let me write it back here. Right, and I have the my map that I can call P upper strict in quotation mark is a map from there to there. And if you think about it, it's naturally written in two steps. The first step, you forget some equivariance, some invariance here, and you go to functions that are just B of K invariants on the same quotient. And then here, you can go from here to here, because this quotient is included into this quotient. And so you restrict the domain of your function. Okay? And it's a fact of life, which actually I want to ignore for now. But this restriction is an equivalence, because you have the so-called Iwasawa decomposition. It's telling you that G of A can be written as B of A times G of O, and therefore, in particular, its quotient is this quotient by restriction. But so even without knowing that, we have this guy appearing in the middle, or maybe I formulate it another way, for a group different from B, where maybe Iwasawa decomposition doesn't hold. So for H, some subgroup of G, my question is now, what is G of A mod G of O? I go back to the interpretation as double quotient mod HK. So by what is, I mean, how can I say what it is in terms of bundles, G bundles on the curve plus something?
What kind of subgroup would you like?
Well, B or parabolics or N or even the trivial group? Just, yeah. Great, so that's a crucial moment actually. Should I stop for questions before I answer?
Your group G, what should be found over?
Yeah, so that's, so I'm characteristic 0, closed field. So,
Completely closed field? Or
yeah.
Okay.
I mean, I haven't changed the field today. I will, but yeah.
So it's a good question that Dennis is asking, but we're not doing this. We are doing more like constant term. Yeah. Is there a reason to consider non-compactified? Yes. Later. Yeah.
So answer to this that allows you to interpret it to move it actually to algebraic geometry is that this space, the quotient, is, for parameterize the spaces, the space of G bundles on X equipped with an H reduction generically. I need to explain what generically means and what H reduction means. Just H reduction, well, let me explain just generically what it is. So in other words, what are those guys? So what is this set? Is set triples of a G bundle on the curve, an open set of X, which I need to take non-empty, and an H reduction of this G bundle on U. Let me write it, modulo some equivalence relation. So that's H reduction of PG on U. So let me explain what H reduction means and what equivalence relation is in this case. So H reduction, just to recall the terminology, I have my G bundle on U. I can write that as a map that I also call P of G from U to BG. And then from BG I have BH. And H reduction is this datum of this lift. So H reduction. Alternatively, I can take the fiber product of this diagram, and an H reduction will be the fiber of the map that goes here. And so what you get is, so alternatively, so that's definition one. Well, actually, that's the definition. Another is just an H reduction is a section of the bundle of homogeneous G spaces, which is obtained by taking PG and sticking in the homogeneous space G of H. So an H reduction is a section here. So that's what you can think of alpha H as this kind of datum. And the equivalence relation, let me just say it in words, is the usual thing that you do when you do generic stuff. So actually, no, let me write it to be precise. So I want PGU. I want to identify the reductions that agree on smaller u. So PG U AH is declared to be equivalent to the same thing, to the similar thing, if and only if on the intersection, which is also non-empty, the two reductions agree. Note that this is a scheme, so I have two maps from a scheme to a scheme, and everything is classical, and then I can ask if they coincide or not. Okay, so that's the definition of this double quotient. The next task is to promote this double quotient to a pre-stack, so to make that into a space of algebraic geometry where we can take the D modules. So now we want to define this as a pre-stack. So I need to tell you what S families of G bundles with a generic reduction are. And the definition pretty much copies this. Well, let's be careful. So to a guy S, to a affine scheme S, I associate the groupoid of triples PG, U, and alpha H modulo an equivalence relation. And now what's PG? That's a G bundle on the product between X and S. And U is the so-called domain, which I will describe in a second. And H of H, alpha of H is, again, it's a reduction of PUG on U. So what is a domain? What I cannot allow arbitrary open. I need arbitrary dense open. So since here I need to be non-empty on the curve, the condition that works is that, so definition, U is a domain. So this is an open in X cross S if domain, if the restriction of U to each closed point, so it's U intersect little s times X, that's non-empty. For any S closed point of S. And note that if I give this definition, when I pull back, so when I define this as a functor, so when I pull back from S prime to S, I get that the pullback of U will also be a domain. Just check this on closed point. Yes?
Oh, sorry. You said for any closed point, but you could also just say any point, right?
This is an open set that's not empty. It doesn't have any empty factors.
Yeah, exactly.
Okay, so
Yeah, why do you?
well, I was going to say, is it the same thing as just saying that U projects trajectively to S?
I guess so, yeah.
Yeah. Just any.
I like this one. Okay, so we have this. And let's give this pre-stack a name. So, by the way, this definition was given by Jonathan Barlev in his thesis. So let's say that's this pre-stack that I just defined. Let's call it the pre-stack of G bundles with generic reduction to B. That's to H. Thank you. So what can I do with this guy, and how does it relate to B bundle? Sorry, to G bundle or to H bundle? That's next question. So note that we have a canonical maps. Yeah, everything is classical because I don't want to get into anything derived and because I'm taking D modules. So anyway, even if I did, it would be a waste of time. So I have a natural map that I can call P enhanced H from a G bundle with generic reduction to a G bundle. I just forget all the reduction just to retain the G bundle. And I also have a natural map that I call IH. Yeah.
Is it true that we can always find a divisor and items quite overrides them, but when we put x times x minus this divisor is included in your U?
Maybe locally. So
Not global.
not globally. Okay. So what are these maps? So this map I said, just take PG, U, and the datum of reduction, just associate PG. And this map, if you have an H bundle, you can consider it, you can extend it, induce it to a G bundle, and it will be canonically reduced to H because I was starting with an H bundle already. Let me make an observation. Sorry?
Just forget the
So I have an H bundle, I produce a G bundle,
Yeah, that's clear.
and then
About pH in
pH, and just so you have this kind of datum, and just remember the G bundle.
And so what's the topology on the U's? This is the Ranspace topology.
Sorry.
What's the topology or the on U?
Just the risky topology.
No.
What do you mean topology?
There's no topology on you.
You just
What do you mean topology?
So you take different U's, right?
yeah, just inclusion. So I'm allowed to change U.
Gary, I think he's confused.
Yeah.
U is a part of the datum, okay?
Yes.
So then the equivalence relation. So you declare it U1, U2B.
Okay.
It's not equivalence relation. Pardon? It's not equivalence relation.
It's not equivalence relation on U's, it's equivalence relation on
No,
V's.
it's not equivalence relation.
So you
it's corresponding to the space.
Oh, it's an equivalent relationship.
you define it on families, and that's a perfect.
Corresponding to the space.
No,
It's
if
back to
PG
clean.
is fixed.
Yeah.
Yeah, so this is the fixed PG, the equivalence relation on the touches U and alpha. For fixed PG it is. So if you forget everything but U, then you're going to get some
You're not going to
the
make
values will
some
be this.
stake
So it'll be take that as a run.
smaller and smaller.
No.
You can't forget everything but you because you can't forget the domain and keep the map. Define a map.
So maybe the way to say this is an equivalent. Maybe a way to say maybe this is an equivalence relation relative to Bungie. So for fixed Bungie, this is an equivalence relation. So I was going to make an observation. So this is the map we care about, but this is a map that naturally we have. And so a little lemma or observation is that for H parabolic, in particular for H equals to B, then this map evaluated on k-value points is an isomorphism, is an equivalent. And the reason is just the evaluatory criterion of properness. Because if I'm on the curve, I'm just asking whether a generic reduction to H, which is like a section, locally a section of so a map from U to G mod H extends to the entire X, and that's true because G mod H, where H parabolic is a proper scheme. So just to emphasize, this is an equivalence on k points, but this guy is dramatically different from this guy as pre-stacks. All right. And by the way, so let me remark that this observation could be interpreted as a geometric analog of the Iwasawa decomposition. So just compare, let me not say more, compare this with this function theory fact, which is the Iwasawa decomposition. So now I can reach ahead and say that this is the main guy and this is the main map that will fix the problem we had before. But before I go and describe that, let's play with this kind of generic data and define by the same token space of generic maps. Define the space of generic maps from X to Y. So X is always my curve, and so Y is a scheme, say. So this is the pre-stack of generic maps.
So X and Y are arbitrary pre-steps. Oh, Y scheme.
Y is a scheme, just for simplicity, Y is a scheme. I will use it in a second. Y is a scheme, X is my curve. I don't change notation. So, but I define this as a functor of points, as always. So to S, we'll map. This is actually easier than what I defined before, but a motivation like this, the other one came first. So again, so what's a generic map from X to Y is you give an open set of X mod S, a domain actually. So let me say domain. And gamma, a map from U to Y. And you're not done because you want to get rid of this domain, so you mod out by the equivalence relation that identifies two functions when they agree on the intersection of the domains. All right, so now we are ready to state the main theorem, which is due to Barlev, Jonathan Barlev. So let's now H is B, H will be B. So I have the map P enhanced of B from band G with generic B reduction to band G. That's this map here. And the pullback from D modulus to band G to this crazy pre-stack is fully faithful. Sorry? Here? Yes. It's fully faithful. So it cures what the problem was. Miraculously, it cures what the problem was before with just the standard map P from band B to band G. And let me say that. So let me make some remarks. First of all, here's another advantage of working with pre-stacks and defining D modules on pre-stacks, that I just gave the definition of pre-stack, and I'm free to take D modules without knowing anything about what this guy is in terms of traditional algebraic geometry. And the second remark is how you prove the theorem, how Jonathan Barlev proves the theorem, is a series of reduction to Dennis contractibility result. And let me start explaining the beginning of it, because we will use the generic maps. And then I will explain what Dennis result is about. So the idea of the proof is to write a very enlightening diagram. So you have band G, you have band G with generic reduction, and then you have band G with generic reduction to the point group. So question for the audience, what is this in terms of, if you want, in terms of the previous talk? So yeah, great. So it's a version of the Grassmann. So G bundles that are trivialized, generically trivialized. So just emphasize generic trivialization. And now a nice exercise is to find out what the fiber product is. So this is my map, P enhanced. So what do we have to compute? We have to compute. So we have a G bundle equipped with a generic reduction to B and a generic trivialization. So I'm allowed to change U, the domains as I wish. So I get, in other words, a G bundle with a generic reduction and on the same U, a generic B reduction. So in other words, this is again a G bundle with generic trivialization times a B reduction of the trivial bundle, which is just generic map from X to G mod B. So it's a fiber square, and that's the projection to the first component. Moreover, I'm trying to explain the argument of the proof, just the beginning of it, so that I can reach this result that I can quote. So we have this diagram, and this arrow turns out to be an étale cover. That's a famous Drinfeld-Simpson.
Étale's rejection.
Okay, yeah. Yeah, sure. That's an étale rejection. So by some formal nonsense, to determine whether this map is fully faithful, I just need to do it here. And here, this map is just a projection. In other words, I'm reduced just need that the pullback, the canonical pullback, I don't know how to say this, P. So P is the stupid map from generic maps to the flag variety to the point. That's the pullback. So I just need to show that this map is fully faithful. And that's AKA, it's equivalent to say that G maps from X to G mod B is homologically contractible. So we take this as a definition. Something is homologically contractible if the pullback of the stupid map from that something to point is fully faithful. And this is very close to Dennis' theorem, which I state, and then I quit. Sorry?
Why is it that? Wait a minute. Étale's rejection. I mean, it's subjective and étale to yes. Okay. It's not étale subjective.
Yeah, so I state Dennis' theorem in a slightly more general form than what it's in his paper, and the extension is due to Barlev. So contractibility is that if so Y is connected and separated scheme, which is a union of opens, each of which is an open, is isomorphic to an open of AN, then generic maps from X to Y is homologically contractible. And so this is actually true for the flag variety. This hypothesis is true for the flag variety, and therefore it's the theorem. That's all I got. Questions?
So it's this is the intended end of the
Yeah, I think, yeah. You agree with that? Then the tutorial is a parallel story. That's why I didn't want to mix it.